So, students, after discussing the topic resistance for a given conductor and the series and parallel combination for the resistance, our next topic is the internal resistance of a given cell. Now, as the resistance offer the obstruction to the flow of current through a conductor, similarly, in the same manner, the internal resistance of a cell also offer the obstruction or resistance to the flow of current through the electrolyte, that is in between the electrodes. As we know that the charged particles are moving from one electrode to other electrode, so this internal resistance of a cell is obstructing the path or restricting the flow of ions from one electrode to the other electrode. Now the factors on which the internal resistance of a cell depends are: number one, the nature of the electrolyte, that is, the material we are using for the electrolyte. Number two, the concentration of the electrolyte. The internal resistance is directly proportional to the concentration of the electrolyte. Internal resistance is directly proportional to the distance between the two electrodes, and it is inversely proportional to the area of the electrodes which is immersed in the electrolyte. And this internal resistance is also inversely proportional to the temperature of electrolyte. Like if we increase the temperature, the internal resistance of the cell decreases, or vice versa. Now let us find out a relation between the internal resistance of a cell, EMF of a cell, and the terminal potential difference between the terminals, that is two ends of the cell, positive and negative. So before finding out that relation, let us discuss a term that is known as the terminal potential difference. Now, as the name suggests, terminal means at the terminal, and potential difference is the potential difference between the terminals. So the potential difference across the terminals of a cell when a current is being drawn from it is called its terminal potential difference. And the symbol for terminal potential difference is V. Now in this case the circuit is closed, but in case of EMF the circuit remains open. So this terminal potential difference will always be less than the EMF of a cell. Now let us find out the relation between the resistance, internal resistance, EMF, and the terminal potential difference. Now in order to find out the relation, let us consider a circuit diagram. So in this circuit diagram, we are having a conductor whose resistance is R, a cell whose EMF is E, and internal resistance is R. A and B are two terminals of the cell, that is the positive and negative terminal. As the cell is providing continuous flow of current to this resistance or conductor, and I be the current across this circuit. Now we know that potential is the amount of work done in bringing a charge from one place to another. So this E, that is the EMF of the cell, is the total amount of work done in making a charge move from this positive terminal to the negative terminal through whole circuit. And here we are having two portions for this circuit, that is, one is connected to this conductor, another one is related to this cell. So this total EMF of cell, that is the total work done, will be equal to the work done in taking the charge from this A through this conductor to B externally in the circuit, and V dash, that is the work done in taking a charge from B terminal to A terminal internally through the cell. Hence total EMF of cell will be V plus V dash. Now applying Ohm's law, as we know that Ohm's law is equals to V equals to IR, where V is the potential, I is the current, and R is the resistance. So applying this Ohm's law for this outer circuit and for this inner arrangement. So we are having V equals to IR, current through the conductor, R is the resistance of the conductor. V dash is the potential, that is difference between terminal A and B, and this is equals to I. The current I is flowing through the cell, and small r, that is the internal resistance of the cell. So therefore E is equals to IR plus IR, and this is the relation. Now we know that Ohm's law says that V equals to IR, and from this above relation we can find out a relation for current, that is I is equals to E by R plus R. So the potential difference V is given by applying Ohm's law. This is equals to ER divided by R plus R. Also we have V is equals to E minus V dash using the first relation, that is this relation. So we are having R from this is equals to E minus V upon I, putting Ohm's law here, and we are having E minus V upon V by R, and this R internal resistance comes out to be E minus V divided by V into R. Now for this we are having special cases from this relation, like when the cell is open, when the cell is closed, how this current or the EMF or the potential difference are related to each other. So in this case, let us consider first case, when the cell is in open circuit. It means no current is being drawn, and we can say that I equals to 0. In that case, when the current is not drawn from the circuit, then the terminal potential difference for open circuit is equals to the EMF of the cell. And the second one, when the circuit is closed, in that case, the potential difference is always less than the EMF of the cell, because when the circuit is closed, then some amount of potential is always dropped across the conductor, across the cell. Hence, it is always less than the EMF of the cell for a closed circuit. Now, after discussing the relation, let us discuss the characteristic curves for a cell. So, let us first discuss the curve for the EMF and R, that is the resistance of a given conductor. Now, the EMF of cell is equals to the terminal potential difference when no current is drawn from the cell. Hence, EMF is independent of this resistance R, and we are getting a straight line for this E versus R graph. Now let us consider the second case, that is V versus R, that is the terminal potential difference and the resistance of a given conductor. Now in closed circuit, there is some potential drop across the resistance. Applying the Ohm's law, we are having V equals to IR, and current, that is we had already obtained the relation for current, and that is E by R plus R. So substituting that, we are having V equals to E by R plus R, that is R, and what we are having, that V is equals to this term, and this is equals to E by 1 plus R by R. We can take LCM, take R above. Now after seeing this relation, what we are observing here, if R, that is the resistance of a given conductor, increases, in that case the potential, terminal potential difference also increases. We can observe from this graph here. For the resistance is equals to 0, that is R is equals to 0, at this position our potential is equals to 0 also from this graph. Here for this position R is equals to 0, as well as the potential is also equals to 0. Now when this R is equals to the internal resistance of a given cell. In that case, we are having the V is equals to, that is the terminal potential, is equals to E by 2. We can obtain this from this relation, putting R is equals to small r, cancelling out, denominator is having 1 plus 1, so V is equals to E by 2, what we are obtaining here. So here from this we are concluding this. Now when R tends to infinity, that is, we further increase the resistance of a given conductor. In that case, this terminal potential difference increases and reaches a value, that is the EMF of the cell, and it cannot go beyond this value, because we know that EMF is the maximum potential for a given cell when the cell is in open circuit. So this is the graph for the closed circuit. Now let us move for third observation, when we are plotting a graph between the terminal potential difference and the current flowing through the conductor. Now as we know that we are having a relation that V is equals to E minus R, or we can write it as V is equals to minus IR plus E. Now let us compare this equation with this equation, that is the equation of a straight line. We are obtaining that slope of this line comes out to be minus R, X is I, that is current, Y is your potential. So we are plotting a graph or taking the observation current along x-axis and the terminal potential difference along the y-axis. So after plotting these, what we are obtaining? We are obtaining 2 points. As according to Ohm's law, V is proportional to current. So we are getting a negative slope, as we had already obtained from this equation. Now for point A, that is for this point A, the current is equals to 0. You can see that for point A, our current is 0. So in this case, our terminal potential difference comes out to be the EMF of the cell. Now for point B, here you can see that the terminal potential difference is 0. So from this relation, if V equals to 0, E is equals to IR. Or from this, we are obtaining that internal resistance of a given cell comes out to be the EMF of cell divided by the current at that particular terminal. And what we are observing from this? We are observing that the slope of this graph, that is VI graph, comes out to be a uniform line with a negative slope. Now, after discussing the characteristics of a cell, let us discuss the combinations of cell in series and parallel. So, as we know that when the cells are combined together, that arrangement is known as a battery. So, a combination of cell is called a battery. Now, in a battery, the cells may be connected in series or in parallel. Like we had already studied the topic for the series or parallel combination for the resistances as well as the capacitors. So likewise, we are discussing the combinations of cells. So let us first consider the cells in series combination. Now for a series combination, the negative terminal of one cell is always connected to the positive terminal of the other cell. Then the negative terminal of this second cell is connected to the positive of third, and so on. So in this manner, we can obtain the series combination of cell for n number of cells. Now, in order to get an expression for series combination of cell, let us consider two cells. Here we are having two cells with EMFs E1 and E2 connected together each other through the series combination. So the negative of one is connected to the positive of the second one. As they are connected in series, so the same current I will flow through the cells. We are considering three terminals, terminal A, terminal B and terminal C, in order to find out the net potential difference across these two terminals. Here R1 is the internal resistance for cell 1, R2 is the internal resistance for cell 2. And again we are considering another circuit which is equivalent to this circuit, in which we are having a cell single whose EMF is equivalent to the combination of these two cells and whose internal resistance is equivalent to the combination of these two resistances. Now let us consider that the potential at terminal A is VA, potential at point B is VB, and the potential at point C is VC. Now the potential across the terminals of two cells will be, let us consider first these 2 points. So between A and B, the potential difference will be VA minus VB. Here we are considering that VA is at higher potential and VB has lower potential, because when the current is being drawn, some potential is being drawn through the cell, and as there is potential drop here, so this will be more as compared to this. That's why we are taking VA minus VB, and this is equals to E1. That is the potential of the cell minus the drop of potential across this cell, that is the current I through this cell and the internal resistance of the cell. Let us mark it as equation number 1. Now let us consider the two terminals, that is B and C. Again, the potential difference across the two terminals B and C will be VB minus VC, and that is E2, that is the EMF of cell 2 minus the current into the resistance, internal resistance of this cell. Mark it as equation number 2. Now, hence the potential difference between terminal A and C for this given combination will be the potential at A minus potential at C. So, we are having that VAC is equals to VA minus VC. And what is VA? That is the potential, or VAB, that is VA minus VB plus VB minus VC. Now let us substitute these values, and after solving this we are getting the terminal potential difference for the terminals A and C is E1 plus E2, arranging the terms, minus I R1 plus R2, and let us mark it as equation number 3. Now this is what we are considering for two cells connected in series combination. Now, as we had already considered that we are replacing these two with a single cell whose EMF is the sum of these two and whose resistance is again the sum of resistance of these two. So let us consider that we are replacing these two cells with a single cell whose EMF is E equivalent, internal resistances are equivalent. So if we compare equation 3 and 4, what we are obtaining? We are getting that E equivalent is equals to E1 plus E2 and R equivalent is equals to R1 plus R2. And now in the similar manner, if we are considering n number of cells connected in series, in that case, E equivalent for the n number of cells will be E1 plus E2 plus E3 and so on till En. And similarly, the internal resistance for the resultant cell will be R1 plus R2 plus R3 plus Rn and so on. So, if we are considering a case in which we are having that n number of cells are connected together each other in series combination, and if we reverse one of the cell, that is for that reverse cell the positive is connected to the positive of other cell and the negative of this cell is connected to the negative of its previous cell. In that case, what we are having, that in that case the equivalent EMF of the cells comes out to be E1 plus E2 plus E3 minus E4, because we are considering that E4 is connected in opposite manner, plus till En. So they obey the additive law as well. Now let us consider when the cells are connected in parallel combinations. So when the cells are connected to the parallel combination, in that case, the positive terminals of all the cells are connected to one point, that is the positive to the positive of cell or either to the negative of cell, and all their negative terminals are connected to the another point, that is the negative or positive of the cell. So this combination is said to be the parallel combination, as all the positive are connected together each other through a single terminal, and all the positive negative respectively connected to the same sort of terminal.